Good evening and welcome to my teacher program, UAE's biggest classroom. And today we have got Ma'am Deepthi Mary Tomsey with us, and she is a teacher from Sharjah Indian School. And today she is gonna give you lessons about grouping of resistors, right? And
Yes.
that is from the unit current electricity, 10th grade physics. And dear students, at any point if you got any doubt, feel free to call us on the number which you can see on the screen. That is the number which you can call us, and 3939 is the SMS number. At any time 24/7 round the clock you can message us for the doubts, and info@ntvua.com, that email ID also you can see it on the screen, and you can email your doubts to that number, which the teacher will be giving you answer through the mails also. And what's the program? It is the unit current electricity, and the portion is grouping of resistors. Welcome, ma'am.
Thank you. Good evening to all the parents and students. Welcome back to teachers program, my teachers program. Today I will be focusing on a topic from current electricity, grouping of resistors, for grade 10 students. Even this topic is very useful for the grade 12 students. Let us begin our class. Grouping of resistors. Grouping of resistors can be done in two ways: resistors in series and resistors in parallel. Let us discuss them one by one. Grouping of resistors. Let us see how grouping of resistors can be done in series. Resistors in series. When do we say that the resistors are in series? When we connect three resistors, let us connect three resistors R1, R2, R3, one after the other, across the endpoints A and B, and let us connect a supply of electricity V across these resistors between the endpoints A and B. Since there is only one path for the flow of current, the current flowing through all the three resistors will be the same. In order to make this concept little more easier, let us remove this source from here and let us mark on at the point A positive, since we know that the A is connected to the positive of the battery, and mark at the end B negative, since B is connected directly to the negative of the battery or the cell. Here you can see that the current flowing through the resistors R1, R2 and R3 are the same, because there is only one path for the flow of current. That means what I meant is, through resistor R1 current is I, through R2 also current is I, and through R3 also the current is I. Now let us see about the potential difference. What do you actually mean by this potential difference? It is the work done in carrying a unit charge from one end of the conductor to the other end. What work is done to carry a unit charge from end A to B is called the potential difference. So we have given a potential difference V across the ends A and B. So this battery or this cell drives the charge across R1, drives the charge across R2, and also drives the charge across R3. The work done in driving the charge across R1, let me name it as V1. The work done to drive the charge across R2, let me name it as V2. And the work done to drive the charge across R3, let me name it as V3. What I meant to say is, according to the law of conservation of energy, energy can neither be created nor be destroyed. So the total work done to carry a unit charge across the ends A and B should be the sum of the work done to carry a charge across R1, the work done to carry a unit charge across R2, and the work done to carry a unit charge across R3. That is, V should be equal to V1 plus V2 plus V3, equation number 1. Now what is this V1, what is this V2 and V3? To get the values of V1, V2 and V3, we will make use of the law called as the Ohm's law. According to Ohm's law, the potential difference is related to current as IR. Since the current flowing through resistor R1 is I, its voltage is V1, and then we can write this V1 as IR1. Equation number 2. Similarly, the potential difference across R2 is V2, the current through the resistor R2 is I, and its resistance is R2. Therefore, V2 is equal to IR2. Equation number 3. Similarly, again the current through R3 is I, the potential difference across R3 is V3. We can relate V3 and R3 as IR3. Equation number 4. What about the situation when you are replacing all the three resistors by a single resistor? If we replace it by a single resistor of resistance Rs, so that the same supply voltage provides the same current across the resistor. What I have done is I have replaced R1, R2 and R3 by a single resistor, which will behave exactly like the three resistors connected in series, so that it is sending the same supply of current, same amount of current using the same source. And according to Ohm's law, we can write that as V is equal to IRS. Equation number 5. And we had written the first equation as V equal to V1 plus V2 plus V3. Into this first equation, if we are substituting the equations which we have written as 2, 3, 4 and 5, how we will get the equation? Let us see. Substituting V as IRS, substituting V1 as IR1, V2 as IR2 and V3 as IR3. We get I common on either side of the equation. IRS is equal to I into R1 plus R2 plus R3. Cancelling I from either side, the effective resistance in series is obtained as R1 plus R2 plus R3. So, what we can say about the law of resistors in series? According to the law of resistors in series, the total resistance in series is the sum of the individual resistances. Thus, we have now seen that how we can group the resistors in series. In general, once again, in series connection, the current through all the resistors will remain the same. The potential difference across each resistor is different, but these potential differences get added up. Because of that, the total resistance in series becomes the sum of the individual resistances. This expression clearly tells you that the total resistance in series is increasing. Because of that, the effective current in the circuit will decrease. Now, before we group the resistors in parallel and discuss more about that, let us go for a short break. Stay tuned, I will be right back.